Hi guys, in this video we're going to be talking about gravity. We're going to look at gravity as a force and talk about the things that affect the strength of gravity and look how orbits work in space and using the thought experiment Newton's cannon, and then we're going to discuss the misnomer of weightlessness. So firstly, gravity. Gravity is one of the four fundamental forces. Okay, so there's four fundamental forces: gravity, electromagnetism, weak force, and strong force. And gravity is a force that occurs between any two objects that have mass. Now this is something that's sort of hard to get your head around because we experience gravity, or the gravity of the Earth. We don't experience the gravity of other things, other smaller things. Because they're smaller, we don't feel that gravity. We can't even measure that gravity. However, there is a gravitational pull on the other object from things, from one to the other. So for example, with that, the Earth pulls a force on us pulling down. We actually pull a force on the Earth as well. It's infinitesimal because it's related to mass and we're much smaller or much lighter than the Earth, but it is a thing. And a good example of this is tides. So we know that the moon is stuck in the gravitational field of the Earth. So that's why it orbits around the Earth. However, we don't think of the moon as placing a pulling force of gravity on the Earth, but it does. And the way that this happens is in tides. So as the Earth spins on its axis, where the moon is affects the tide. So the gravitation of the moon pulls the water from these low tide positions. So it pulls the water from the sides of the Earth relative to the moon up to the moon, so that you get a high tide where in line with the moon, and you also get a high tide on the other side from this effect of pulling at the sides, but this high tide at the bottom won't be as big as the one at the top, which is why over a day period you have two high tides, one larger one and one smaller one. Now, how strong gravity is affected by two things: mass, being how much matter an object has, and proximity, or how close they are to one another. Bigger, rather more massive objects have more gravity, while objects closer together have more gravity. So if we look at, to compare here, Earth, Venus has a similar gravity to that of Earth. Mars, on the other hand, has about 1/3 or 1/4 of the gravity of Earth because it is smaller and less massive. Massive being in the sense of having mass. And the moon over here, we're looking at about a bit less than 1/3 of the mass of the Earth, which is why when you see the videos from space and they're jumping very, very high, or much higher than they'd be able to jump on Earth, even though they're strapped down with all that gear. Now there is an equation that you can use to calculate the effect of gravity of two objects, and this is it over here, where the force is the gravitational constant times the two masses divided by how far away they are from each other. You don't need to know that, but there you can represent this strength in a numerical way using that formula. Okay, orbit. When a smaller object is traveling around a larger object, we refer to this as an orbit. So for example, the moon, smaller than the Earth, it orbits around the Earth. The Earth orbits around the sun along with all the other planets. So these are orbits. And it's to do with speed. Now to explain how orbits work, we'll use a thought experiment called Newton's cannon. So the idea here is that Newton said, okay, what if I have a cannon and the cannon's on top of a big hill? Now if I fire that cannon, it's going to go a certain distance, and then the gravitational pull of the Earth is going, so the cannon is being fired perpendicularly, or tangentially to the Earth, so it's going this way, out that way. But because of gravity of the Earth, it's going to have a force pulling this way down to the Earth. So as it goes out, it's going to get pulled down by gravity and eventually hit the Earth. And he said, well, what if that cannon was even stronger? What if that cannon was so powerful that the horizontal velocity, so the speed at which it's going that way around the Earth, is so fast that the pull of the gravitational pull of the Earth, pulling it down to the ground, is equal to the speed at which the Earth curves. So this means that while it's being pulled, so at this point it's being pulled in this direction, but it's moving in this direction, and it continues around this here, it's being pulled in this direction towards the Earth, so it's going to move in that direction, and it does, but the Earth curves at the same speed, so it takes this orbital path around the Earth. So if that's not quite at that orbit, and there's a couple of different orbits that you can have, but if it's not quite at that orbit, it's a bit slow, it will crash into the Earth, and if it's a bit fast, it will fly out into the solar system. So you won't be able to get that into orbit if it's too fast. And the speed at which it flies out into the solar system is what we refer to as escape velocity. Now we talk about weightlessness and being in space and having the feeling of weightlessness, and you would have seen videos of like on the International Space Station where people are just floating around. Now this is a bit of a misnomer because you still have weight, it's just that that weight is being pulled in various directions. So you still have mass, and the weight is the mass and the gravity that's on the mass. But it's actually, what's actually happening is that you're in free fall. And like that cannonball is in free fall, constantly falling towards the Earth, but because it's moving sideways so fast, going around the Earth instead, this perceived weightlessness is this constant free fall that you're in. Now, a skydiver or a cannon on the Earth would have friction from the atmosphere. However, if you're in space, which is a vacuum, there's no friction from the atmosphere, so you can't feel the wind rushing past you. In addition to this, if you're, for example, inside a spaceship or the International Space Station or whatever it is that you're hanging around in space, all the things around you are falling in that free fall at the same speed that you are. So your reference, you see things around you as if they're stationary. However, they're actually falling towards whatever gravitational mass it is that you're falling towards. This can be likened to the Earth moving around the Sun. Okay, so the Earth is in a state of free fall towards the Sun, so being pulled by the gravitation of the Sun, but because of that perpendicular motion, it's traveling around in an orbit. So we're actually traveling thousands and thousands of kilometers every year, so in the orbit around, and it's many, would be millions actually. The Earth itself is traveling really, really fast. However, we being on the Earth as it's traveling, and the buildings that we're in being on the Earth, and everything around us, the atmosphere being stuck to the Earth, we don't feel like we're actually moving at all when we're sitting still. Even though the Earth is moving through space, and the solar system is also moving through space as it rotates around the supermassive black hole in the center of the Milky Way. In this video, we've talked about gravity as being one of the 4 fundamental forces that occur between any two objects that have mass, the strength being related to both that mass and the distance that those two objects are apart. We talked about orbits being one object rotating around another object, and the thought experiment of Newton's cannon. And we talked about how weightlessness isn't really the right word for what you're feeling, and that that's actually in a constant state of free fall. You just don't notice it. Thanks for watching, guys. Peace out.